Baby shark do 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 baby shark. Good evening. Welcome to another episode, and today we will be discussing Fermat's little theorem. Right, so before I begin the video, I would like to first of all make sure that you do not confuse this with Fermat's big theorem, which is quite more complicated, as you all must know. Okay, so now let's begin with the statement of the theorem. So Fermat's little theorem states that if P is a prime number, and we have the other condition that P does not divide A, which means that the GCD of P and A is 1, then we have that A to the power of P minus 1 is going to be congruent to 1 mod P. Alright, so now let's move on to a motivating example which will show you how this theorem actually works. What we're trying to answer is, what is the remainder when 4 to the power of 100,000 is divided by 7? Now, this is an extremely humongous number. For some context, there are 4 to the power of 125 atoms in the visible universe, and as you can see that, well, I cannot emphasize how big this number is in comparison to that, and we cannot solve this question by regular long division. You can try it, but I don't think it will work. So we'll need to use Fermat's little theorem here. In this box over here, I've written down the statement of the theorem, which is that if P is a prime number and P does not divide A, then we have A to the power of P minus 1 is congruent to 1 mod P. And with that in mind, let's now begin the solution of this question. So we need to solve for the following congruence relation, which is basically that 4 to the power of 100,000 is congruent to x mod 7, and we know by Fermat's little theorem that 4 to the power of 6 is congruent to 1 mod 7. Okay, so this is what we know. This is what we need to solve, and this is what we know. Okay, and so the first thing that I will do is I will break this 100,000 and divide it by 6. So as you know, by the regular rules of division, that whenever we divide a number by another, there's always going to be a quotient and a remainder. In this particular case, it's going to be, so 100,000 upon division by 6 is equal to the following: 6 to the power of 16,666 plus 4. And now what we can do is just break this down. So we need to solve is congruent to x mod 7, right? And now we can write this expression down in the following way. So we have 4 to the power of 6 into 16,666 plus 4 is congruent to x mod 7, and then we can break this down in the following way: 6 into 16,666 into 4 to the power of 4 is congruent to x mod 7. But we know that this entire expression over here is going to be congruent to 1 mod 7 by Fermat's little theorem. That's because if 4 to the power of 6 is congruent to 1 mod 7, then any power of this, like for example 4 to the power of 6a, is also going to be congruent to 1 mod 7, because we will simply just repeat that permutation another time. So this whole expression over here can be reduced to 1 mod 7, and here we have 4 to the power of 4 is congruent to x mod 7, and so 4 to the power of 4, which is 256, is congruent to x mod 7, and now we just need to reduce this expression modulo 7, so we divide this by 7 and we get a remainder of 4. So this 256 is congruent to 4 mod 7, and thus the remainder when 4 to the power of 100,000 is divided by 7 is in fact equal to 4. Alright, so now let's move on to the next example. Right, so now let's move on to the second example, the second application of Fermat's little theorem. We need to find all the roots of the polynomial x raised to the power p is congruent to 1 mod p. Again, for your convenience, I have written down Fermat's little theorem, and we will use this in addition to another lemma, which I will prove right now. So the lemma states that the equation a squared is congruent to 1 mod p has solutions if and only if a is equal to 1 or a is equal to p minus 1. Okay, so let's begin the proof of this. We need to show that a squared is congruent to 1 has only the following solutions. So we have a squared is congruent to 1 mod p, but that means that a squared minus 1 is congruent to 0 mod p, and that means that p divides a squared minus 1 just by the definition of linear congruences, and this can then be broken down or factored into p divides a plus 1 and p divides a minus 1. Now we know by an earlier lemma, which I will just write down over here, that if p divides ab and p is a prime number, then it must be the case that p divides a or p divides b. And so from that lemma we can now conclude the following, that p either divides a plus 1 or p divides a minus 1. So in the first case we have, if p divides a plus 1, then we have a plus 1 is congruent to 0 mod p. Again, this just again follows from the definition, and we have a is congruent to minus 1 mod p. And in the second case, if p divides a minus 1, we will have a minus 1 is congruent to 0 mod p, in which case we have that a is congruent to 1 mod p. Oh, and one thing that I would like to just highlight over here is that if a is congruent to minus 1 mod p, that is the same as saying that p minus 1 is congruent to minus 1 mod p. This is because by the definition of congruence modulo n, we need to, if p divides a minus b, then two numbers are congruent, and in this case we have that p minus 1 plus 1 is congruent to 0 mod p, which is clearly true because p divides itself. So thus we have now shown that we have shown that the following equation, a squared is equal to 1 mod p, has solutions if and only if p is equal to 1 or p is equal to p minus 1. Right. Begin the solution of this question. Again, I have written down Fermat's little theorem along with the lemma which we proved earlier. here on the side. And let's begin. So we have to find all the roots of the following polynomial. X to the power of p is congruent to 1 mod p. So we can rewrite x to the power of p in the following manner. X to the power of p minus 1 times x is congruent to 1 mod p. But this we know by Fermat's little theorem, that as long as p does not divide x, which we're taking for granted here because otherwise it would just be the trivial case when x is equal to 0. So assuming that p does not divide x, we have that x to the power of p minus 1 is congruent to 1 mod p, and we have to now solve the equation x is equal to 1 mod p. But that we know from this lemma over here, that has solutions if and only if x is equal to 1 or x is equal to p minus 1. And that concludes the solution to this question. If you enjoyed this video, and in the next video I will be presenting the formal proof of Fermat's little theorem. So see you until then.